Now that we've had a look at radiation, we're going to have a look at the reactions that occur when we radioactively decay. The first type of decay we're going to be looking at is alpha decay. When we look at our graph, we can see that alpha decay occurs up here, where there is quite a high number of neutrons and protons. So when it decays, it's trying to get rid of as many protons and neutrons at the same time. To do this, it releases a helium nucleus. We write this as just an He with a 4 for the weight of the atom and 2 for the number of protons. Now, the alpha particle, the helium nucleus, doesn't actually have any electrons, so it actually has a +2 charge. Now let's look at our beta decay. Well, that occurs down here, where our protons and neutrons are roughly about the same. However, it still occurs at higher levels of neutrons to protons. The first one we're going to look at is beta plus decay. As this graph shows, it's reducing the number of protons. It's pushing it closer back to this line. So our beta plus is taking a proton and it's changing it into a neutron. But we need to balance it. So we've got a positive charge over here, so we need a positive charge on this side. Well, we're just going to add a positron, which is the same as an electron, but is positively charged. The other thing it releases is called an electron neutrino. Now, in a way, that's just energy, but you'll come across that more in semester 4. So now let's write this down simply. Our proton changes into a neutron plus a positron, which we denote the same as an electron, but we put a positive charge on it, plus an electron neutrino, which we write as VE. Now let's look at beta minus decay. Well, that occurs when we have too many neutrons. So it's going to change a neutron into a proton. However, that hasn't balanced our equation. Over here, we have a neutron which has no charge. Over here, we have a proton which has a positive charge. So that means that we need to add an electron to it, which has a negative charge. Now we have no charge on this side, as well as no charge on the other side of our equation. However, just like with beta plus decay, which had the electron neutrino, we also have to take into account the energy that is coming out of this reaction. And with that one, we have an antineutrino. An antineutrino is very similar to that of an electron neutrino. This is just conserving our energy and our momentum from our equation. However, seeing that we've created an electron neutrino in this equation, our beta plus, there has to be an opposite to it, and that's created in our beta minus, which is the antineutrino. Now, writing the equation for this one is our neutron becomes a proton plus our electron, which we give a negative charge, plus our antineutrino, which is just denoted by a negative sign there.